An easy way to learn is learning by example. So the exercise for 1 of worksheet 2 is now our guide to learning how to use the T-stat and F-stat in practice. So suppose we have the following model that explains baseball players' salaries. So what explains players' salaries? It's of course an intercept, but it's also years played in the league. It's games per year, batting average, and home runs per year, and runs batted in per year. Okay, so the salary is 1993 salary, and we gather data to estimate this regression. This is the population regression, and here is the estimated regression with the sample coefficients. So for example, this is the beta naught hat, and this is the standard error of the intercept. Okay, the sample intercept, because it's based on us taking a random sample from a population of baseball players and estimating the coefficients. So here we have that n is our number of observations, and SSR is the sum of squared residuals. You're just squaring the residuals, the actual y value minus the fitted value, the salary hat, and square it, and you do that, or you add up all the 353 residuals to get 183. And the r squared is 0.6278. And what we would like to know is whether or not some of these slopes are different from 0. Okay, so our first test is the beta 3, the slope for batting average is the slope for batting average different from 0, and in our hypothesis we always make the alternative hypothesis first, and we say that, well, we believe that batting average, the slope on batting average is different from 0, which means that we believe that batting average is a relevant metric to understand the salary of baseball players. So the alternative hypothesis is that batting average does not have anything to any impact on the salary. So it's the true. We believe that the true or the alternative hypothesis is that the true effect of batting average on salary is 0. Okay, the slope is 0. Okay, so we would calculate the t statistic. As such, we take the sample slope, okay, minus the hypothesized value, the null hypothesis. This is a difference. Okay, so we measure the difference, but we want this difference to be in units of the standard error. Okay, So that's why we divide it by the standard error of the sample slope. So what we do is that we have, as is measured, or as a have shown in a different video, is that we have the hypothesized beta here. We have the sample slope here, and the sample slope is quite small. It's 0.00098, and we have to figure out, are these two far apart or not in probable terms? Okay, in probable terms. And if they are 1.96 standard errors away from each other or more, then we say that, well, our result is unlikely to come about at random. So we reject that we reject the null hypothesis of beta 3 equals 0, and keep the alternative hypothesis that it's different from 0. But in our case, the standard error is, let's see, 0.001. Okay, so it's actually here, like this. One standard error, okay, which means that this difference is 0.00098 divided by 0.0010 is 0.98 standard errors. So this is 0.98 standard errors distance between these two values. And as such, we do not reject the null hypothesis because they are too close, right? Okay, what about the beta 4 and the beta 5? Well, we can do the same test for them because this is only, we only have one equation in the null hypothesis, so we can we can use the t-test on those hypotheses as well. So we could calculate the t-statistic as the obtained value, the sample coefficient value, minus the null hypothesis, the hypothesized value of the true slope, divided by the standard error to get this distance in standard error terms, which means that in this case we get 0.894 standard errors of distance between the obtained value from our analysis and the hypothesized value. So we cannot say that beta 4, the slope on the home runs per year is oh, sorry, there should be hats here. So we cannot say that this is not by a random chance. Okay, This distance is likely just by random chance. So we do the same for the fifth variable, and neither in this case can we reject the null hypothesis, which means that we cannot reject any of these as being different from 0, which means that we are led to believe that these metrics, these random variables, they are not useful in explaining the y variable, which is the level of the salary. But how would we test the hypothesis that if we control for the games per year, then these variables have no effect on salary. Okay, so what we do is that to test these as a group, we say that the null hypothesis is the slope on the third variable is equal to 0. At the same time, the slope on the fourth and the fifth variable is equal to 0. So it's a joint test on these slopes being equal to 0. And the alternative hypothesis is then that at least one of beta 3, beta 4, beta 5 is not equal to 0. Okay, so the common pitfall is to test them one by one, but then you do not control for the other variables because you can let them vary, right? So we need to test the joint distribution of these sample slopes, and what we do is that we can use the f-test. Okay, so as you saw that when we tested these slopes individually, we could not reject any of them being different from 0, but as we will see, if we take a joint test, then we can see that they actually help us in explaining the level of the salary. So to carry out this joint test, we use the f-stat, and quite important, the population regression errors are assumed to be homoscedastic. Okay, if we use this formula, then the regression errors are assumed to be homoscedastic, or need to be homoscedastic. So what we do is that we take the f-stat and we calculate we run a regression to get the f-stat. We run a regression, and we run a regression such that we get the sum of squared residuals. Okay, and we do this for a unrestricted unrestricted model, and we do this for a restricted model. So you can also write this as SSR restricted minus SSR unrestricted divided by SSR unrestricted times n minus k minus 1, you just multiply this first expression with q times n minus k minus 1, okay? And then you have q here. Okay, so you can split this up into two parts. Okay, so let's look at each and every one of these parts. The SSR is the sum of squared residuals of the restricted regression. Okay. Restricted means that you set some bounds on some of the coefficients. In this case, we have set bounds on 3 coefficients, which is the beta 3, beta 4, and beta 5. We set them to 0. Okay. When we set them to 0, we can look at the original equation, here, and we, if this is 0, this is 0, and this is 0, then these variables, they have no impact on the salary, which means that we are only left with these variables, right? So then this whole regression is the unrestricted regression, and this would be the restricted regression. Okay, so let's continue. So SSR is the sum of squared residuals from the restricted regression. Okay, and the restricted regression, it only contains these two variables, and the sum of squared residuals is often included in the regression output that you get from your statistical software. Okay, the sum of squared residuals unrestricted is the full model, right? So that's why it's unrestricted, because we let all the slopes vary and take on the optimal value according to the ordinary least squares method. So Q is the number of restrictions in our hypothesis test, and in this case we have 3 restrictions, 3 slopes that we set to 0, which means that Q equals 3. N is the sample size, and K is the number of regressors in the unrestricted regression. Sample size is 353, and K is the number of regressors in the unrestricted regression. This is number of regressors is number equals number of slopes. Okay, so we have 353. So n minus k minus 1 is 353 minus 5, because we have 5 regressors in the full model, minus 1. So the intuition behind the fstat is that one of the parts of the fstat was the the after we split it, right, is that the sum of squared residuals of the restricted model minus the sum of squared residual of the unrestricted model divided by the sum of squared residuals of the unrestricted model, it really gives you the relative change in sum of squared residuals from the unrestricted model to the restricted model, right? So it's a proportional change, and you have to understand that the restricted model, it will provide a worse fit than the unrestricted full model, which means that the sum of squared residuals for the restricted models is bigger than for the unrestricted model. Okay, so if the increase in the size of the dispersion of the residuals, the sum of squared residuals, is large enough, then we say that these variables jointly provide such a better fit if they are included in the model, that jointly they should be in the model. Okay, let's mention some important stuff about the f-stat. The SSR, the sum of squared residuals for the restricted model, the one with the fewer variables, is always greater than the sum of squared residuals for the larger unrestricted model. This means that the f-stat is always positive, which means this is a simple test, which means you can, if you get a negative f-stat, then you're doing something wrong. Okay. Also, Q, the number of restricted coefficients, is the degrees of freedom in the restricted model minus the degrees of freedom in the unrestricted model. So here you can just take the degrees of freedom in the restricted model minus degrees of freedom in the unrestricted model, and you get the number of Q. And n minus k minus 1 is the degrees of freedom in the unrestricted model. Okay, so let's calculate the f-stat. We are given that the SSR in the restricted model is 198, and we were given in the output that the sum of squared residuals in the original model, the bigger model, is 183. Then we see that we get the difference, or the relative difference between these two sum of squared residuals, and we add to that the 353, the n minus k minus 1 divided by the d, the number of restrictions. Okay, and we get the number of 9.55, and we have to know, is this large or not? What we do is that we compare it to a critical value. Okay, we have to compare the f-stat to a critical value, and for large n, like above 300 or 250, then we can assume a kind of a underlying normal distribution, but the F distribution with infinite degrees of freedom, and we have to supply the number of restrictions. Okay, so here we have the number of restrictions. Okay, so in this case Q is 3, so we find from either a F table or from Stata that for a test at the 10% significance level, this critical value is approximately 2.08. And since our value is larger than the critical value, then we reject the null hypothesis. So what we find is that we reject that all these slopes are equal to 0 jointly, and we can say that at least one of them is different from 0. So if you look at the null hypothesis, it was jointly that all of them were 0, and the alternative hypothesis was that at least one of the slopes are different from 0. So now that is under the way. So to conclude, that the formula we used for the F test, it's only valid under the assumption of homoscedasticity. If we have heteroscedasticity, then we have to use a robust F statistic. However, it's not as easily computed. So so we are not deriving this here, and what we can think of is that we just rejected the joint hypothesis that these three variables have no effect on salary. If we had looked only at the individual t-values, then we would have failed to reject the null hypothesis, and we would have been led to believe that these variables should not be in the model. So what might explain this case? Well, the reason why the individual t-stats are low is because home runs per year and runs batted per year, batted in, are highly correlated. Okay, and remember from our previous video on multicollinearity that if variables are highly correlated either on the positive or negative side, then it's very difficult to estimate their individual slopes, because their slopes will on average be correct, but the standard errors will be very large. So that's why F-stats are useful for testing the significance of a group of fairly correlated variables. So a last example in this video is that suppose we want to test whether firm performance affects CEO salary. Okay, and there are many ways to measure firm performance, and they are often very highly correlated, positively correlated. And the F test would then be a nice way to be able to keep all these variables in the model, and you would be able to test them jointly to see whether or not they have a significant effect on explaining the CEO salary. So, see you next time.